Okay, let's start. So last time we introduced the axiom of choice, which said the following. For all sets I and indexed systems A sub I where I changes in this index set such that A is non-empty. For all I, we have the following. So the axiom of choice tells us that if you have a collection of sets which are all non-empty, then the Cartesian product is non-empty. And when I say Cartesian product, I mean the generalized Cartesian product, like the product of an index system of sets. Now, this is the form of the axiom of choice I introduced last time. I did this because we're talking about generalized Cartesian products, products of an arbitrary collection of sets, and like this statement, whenever these are empty, this product should be non-empty. I think it's like intuitively obvious. There are equivalent forms of axiom of choice which are not as intuitively obvious as this one. So this is why I went with this. Most of the time we're going to use the following form of the axiom of choice. This is actually equivalent to axiom of choice, but I'm just going to prove it as if it's like a consequence. So let M be a set whose elements are non-empty sets. So I have this M, and M has its members, and the members of M are non-empty. So what I want to do is the following. I want to choose one element from each set in M. So this is my, think of this as my collection of sets. These are non-empty sets. I want to choose one element from each one. So what does it mean to choose an element? It means, well, I want to choose one element from this guy. What do? I want to say that like from this set I chose this element. I can do that with a function which takes this set to this element, and let's say this set to this element, and this set to this element, and this set to this element. So each set is mapped to one of its elements, and this way you can choose an element from each one. So I want to do this. Okay, the axiom of choice guarantees that I can do this. So let M be a set whose elements are non-empty sets. Then there exists a function. Now, I want to construct this function. Let's look at the domain and range of this function. The domain should be obviously M. Okay, so each element of M will be mapped to something. Well, where are these guys coming from? These guys are coming from the union of elements of M. Okay, so I need to take the union of M. What is this? This is the set consisting of elements of M. Okay, so this is basically the union of, this set is the union of elements of M. So I want to have a function satisfying this property such that for all x in M, such that f of x is an x for all x in M. For every element in M, I want to choose one element from that set. Okay, so f of x chooses, this is my f of x is an element of x. F chooses one element from x, okay? Now this is the form of the axiom of choice we use in practice a lot. Let's prove this. This is actually almost equivalent to this form of axiom of choice, but this is like in terms of index system of sets and so on. So let me just prove this by observing that I can just think of every set as an index system of sets, okay? So we can index any set by itself via the identity function. Now, what's an index system of sets? What is this? This is like supposed to be some function from this index set to something. And the something contains all these sets AI, okay? Now, notice that I can just turn any set into an index system of sets by the identity function. So, more precisely, let's do this. Let my index set be M, and I construct the following index family. This is my index family Mi. So it's my index system of sets with Mi equals I for all I in my index. So basically what I did was, this is my set M. I chose this as my index set, and I look at the identity function on this. So I'm basically, now I'm not looking at this choice function. So I'm looking at the identity function. Everything is mapped to itself. Okay? So this creates an index system of sets. And I want to apply the axiom of choice. Each of these guys are non-empty by the assumption over here. Since this is true, by the axiom of choice, there exists some map from here, well, from the index set to the union of M, such that f of I is an I for all I in M, which equals M. Sorry, for all I in I, which equals M. Now remember the definition of this. What was the definition of this product? This was the set of functions from the index set to the union of these AIs such that f of I is an AI. I choose my AIs, MIs, to be, well, I choose my AIs to be elements of M. Okay, so Mi is I, and I is changing over M. Remember this index set is M. So any element from this will satisfy the relation f of I is an I. Okay, this is by definition of this. And I know that there exists such a function because existence of this function is the same as this product being non-empty. Okay, so by axiom of choice, I have such a function, and this is what I wanted to prove. And we can prove the other direction as well. If you start with this, you can prove that this is true. So this is another form of axiom of choice. The only reason I introduced this one is this is like that axiom of choice is true, whatever that means, is more obvious in this form. Like we're basically generalizing the concept of Cartesian product, and that Cartesian product of two non-empty sets is non-empty should generalize to that generalized Cartesian product, okay? But this is the form of the axiom of choice we use a lot in practice. How do we use this? Well, I'm going to show you an important example. which shows the survival strategy in a hypothetical game of prisoners. But that's going to come next lecture. In order to show me that, we need to talk about equivalence relations. So let's start that. And this is an important concept on its own. I'm not doing this just because that puzzle I'm going to introduce next time. So let's start talking about equivalence relations. Before that, any questions about this? Now, we're going to talk about the importance of this later, but for now, we should know the following. Axiom of choice tells you that if you have a collection of sets which are non-empty, then you can choose one element from each one. Equivalently, if you have an index system of sets, all of which are non-empty, then the product is non-empty. Okay? Later on, after we introduce ordinals and transfinite induction, I'm going to give you two more equivalent forms of axiom of choice, namely the Zorn's lemma and the well-ordering theorem. Those are going to come later. And when I say equivalent, I mean the following. When I say these are equivalent, I mean this. Take the other axioms as axioms, then you can prove that this holds if and only if this holds. And we just proved one direction. Anyway, let's start talking about equivalence relations. So we have the universe of mathematical objects, namely the sets. In practice, for various purposes, we want to consider some of these objects which are not equal to be equivalent. Okay? Notice the difference between the word equal and equivalent. As sets, two sets are either the same, they're identical or not. But in practice, sometimes we want to consider them to be equivalent. For what purposes? For example, take this set, okay, and take this set. A and B are arbitrary sets. You can put a group structure on this. Define the multiplication by this multiplied by itself as itself, this multiplied by B as B. And do a similar thing over here. Now these are all isomorphic to the group Z2, cyclic group of order 2. We want to consider these the same. How do we do that? We look at the isomorphism relation, whatever that means. Now, up to isomorphism, these are the same. They're not the same sets, but they're the same group, whatever the same group means. It means that, like under isomorphism, these are the same. But what does that really mean? It means that when you put all the isomorphic objects together, you look at that class of sets, a class of groups which are all isomorphic as one object. Now, in order to do that, in order to talk about such things like I'm putting all the objects which are isomorphic to the same class, use the notion of an equivalence relation. Okay? The point is, we're going to take objects which are not equal, which are distinct, and we're going to consider them as the same up to some rule, whatever that rule is. Okay? So, definition. A relation E on a set X. Now, when I say a relation on a set X, what did that mean? We learned this last time or maybe before that. A relation on a set X means that this is a relation from X to X. Okay, it's a subset of X cross X. A relation E on a set X is said to be an equivalence relation if it satisfies the following properties. Now, you learned about these, I guess, in 111, but it's been 2 years or maybe 1 year since you learned it, so you might have forgotten it. Let's go over these very quickly. E is supposed to be reflexive. What that means is that for all x and x, x should be related to x, okay? So this is, as you know, another way of writing XX is an E. E should be symmetric, meaning that for all x and y in x related to y should imply y related to x, and E should be transitive. And transitive means for all x and x, for all y and x, and for all z and x. I don't know why I'm writing it this long. X related to y and y related to z should imply that x is related to z. Okay. Now, a relation satisfying these is called an equivalence relation. What's an example of an equivalence relation? Maybe I should write over here. The identity relation on any set is an equivalence relation for all sets X. Remember, this is the relation consisting of all ordered pairs XX, where X is an X. Indeed, you can easily show that this is a subset of any equivalence relation, okay? Take any equivalence relation E on a set X, then identity relation is contained in it because of the reflexivity, okay? This guarantees that the identity relation is a subset of your relation. What's another example? So let A, B, C some sets, okay, and look at the three-element set A, B, C, and then the following is an equivalence relation. Okay, you can just check this. Oh, sorry, I forgot BB. You can check that this is reflexive, symmetric, and transitive. Okay, there are finitely many cases. You can check them by hand. So let's go back to the motivation behind these. We said that we wanted to consider certain objects to be the same, even though they're distinct, like as sets they're distinct, but we want to consider them as the same for various purposes. And this does that, like everything should be considered the same as itself because it is literally the same. And if you're considering X as the same as y, then y should be considered the same as x, whatever the same means. And similarly, our intuition of being the same is transitive, meaning that if x is the same as y and y is considered the same as z, and then x should be considered the same as z. So this captures, well, this notion works for our purposes, namely the purpose that we want to put certain objects together and consider them the same. That rule, according to which we're going to consider the objects the same, is the relation. Like it's the definition of this E, whatever it's going to be. And while motivating this notion, I also talked about we're talking about groups. Let's put all these isomorphic groups together in this class, blah blah. Now, how are we going to do that? I've just introduced a formal notion. So using this, let's try to define how we can put all these objects together which are considered the same. In order to do that, we need to talk about equivalence classes. Let me make the definition. Let X be a set and E be an equivalence relation. Okay, I'm just gonna write equivalence relation. Okay, I don't want to write too many symbols on the board on X. And let's fix an element of X. The equivalence class of little x under E is the set. Now we show the equivalence class of x under E like this. It's the set of all y such that x is related to y. By symmetry, it doesn't matter whether I write y is related to x here. By reflexibility, by the property of being reflexive, this is always non-empty, namely it contains x. And what is like the property of transitivity, what is it going to do? We're going to see that in a second. Okay, so some terminology. Two elements in an equivalence class are said to be equivalent. Okay, so if you have an equivalence relation, if you have an equivalence class, then two elements in the same equivalence class are said to be equivalent. Okay, what else? Blah, blah, blah. Let's not do that. I don't need that. Okay, I think I can assign two exercises, not related to this, but related to the notion of equivalence relation. Oh, here's a question. What if I choose my x to be empty over here? If x is empty, then x cross x is empty. So if there is any equivalence relation at all, it should be a subset of the empty set, which can only be the empty set. So if x is empty, the only possible relation on it is the empty relation. Does empty relation satisfy all these properties? Yes. If you put x equals empty set here, remember what this was. This was a shorthand for all x. If x is an x, then x. If you put x equals empty set here, then this is vacuously true because it's an if-then statement and the premise is false all the time. So this is automatically true, and so are the other two properties. So the empty set is an equivalence relation on the empty set. Okay, now what are the equivalence classes of the empty relation? There are none, because if you look at the definition of an equivalence class, I choose an element from the underlying set. In order to talk about equivalence classes, equivalence classes of an equivalence relation, I need to have elements around. So when x is empty, I have the empty relation, which is an equivalence relation, but it's like it doesn't have any equivalence classes. Okay. Anyway, just so you digest the concept of an equivalence relation, let me assign two exercises. Okay, let X be a set whose elements are equivalence relations on a non-empty set Y. So I have a set Y. This is non-empty. I have equivalence relations on Y. Like, why do these exist? At worst, I have the identity relation. So there are equivalence relations on Y. I take some of them, okay? And I put them in the set X. X is a set. Its elements are equivalence relations on an empty set Y. Now prove the following. Whenever you choose two equivalence relations from X, if it is the case that one of them is a subset of the other, then the union of the set is an equivalence relation on Y. What this says is, forget about all the symbols. If you have a set, if the elements of this set are equivalence relations, and if it is the case that given any two, these are always comparable in the sense that this is a subset of this one or this is a subset of this one. If this is true, then when you take the union of all these equivalence relations, you get an equivalence relation. This in particular implies the following. You can obtain this as a corollary. Okay. Let's say that you have the equivalence relations, E1, E2, E3, dot, 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 and let's say that these are subsets of each other. I don't want to use this, you understand what this means, right, intuitively. So I'm just going to abuse the notation and I'm going to do stuff like this. If these are equivalence relations on a set X, then so is this union. Now, I don't want to write this because at this point we don't know what the set of natural numbers is, but pretend that you know it, okay? The point is, if your equivalence relation is going to fix at X, and if these are increasing, if these are subsets of each other, then the union is an equivalence relation, okay? So that's like a corollary to this exercise. One more exercise. This is a simple one. Okay, I need to be quicker. I was planning to finish talking about partitions today. This is a simpler one. This is just to check that you understood the definition. Let X be any set and E be the relation defined by the following. There's a bijection from X to Y. Now show that this is an equivalence relation, is an equivalence relation. Pick any set, look at the relation on this set defined by the following. Two elements of this set are, this is like little x. This is defined like this for all x, y, and x. Two elements of this set are they're E-equivalent, they're in the same equivalence class, if and only if there is a bijection between them. Show that this is an equivalence relation, okay? You're just going to double check the properties. Obviously, everything is related to itself. We have the bijection identity function. You can check that this is transitive because composition of two bijections is the bijection, and you can double check that this is symmetric because the inverse relation of a bijection is also a bijection, okay? Now, let's come to the actual use of these equivalence relations, namely partitions of a set. Before defining it, I'm just going to prove a lemma, which is going to be useful. Let X be a set. Well, let's make this non-empty. And E be an equivalence relation on this. So I have a set which is non-empty, and I have an equivalence relation on this. Then if I take two elements of this set, either, maybe, yeah, I should put either here. We have either this or either the equivalence classes of these elements are the same or they're disjoint. So let's do the proof. This is just going to follow from the definitions. So let's pick two elements, which we can do because we're working with an empty set. Now we want to prove that either this happens or this one happens. Clearly, these equivalence classes are non-empty because x is in here and y is in here. Thus, well, okay. I didn't have to write that, but whatever. Anyway, let's start with the following case. Yeah, I didn't need this. Okay, let's start with the following case. Let's say that x is related to y. I want to prove that if this happens, then this is the case. Then case 1, we split into cases. Case 1, x is related to y. Now in this case we wish to prove the following. We wish to prove that the equivalence classes are the same. How do we show that two sets are the same? We show that they have the same elements. So let Z be an equivalence class of x. Then, by definition, how would I define equivalence class? Okay, let's go like this. By definition, we have that. Well, this is symmetric, and so this relation is symmetric, so I can do the following. I have Z is related to x. Now by transitivity, Z is related to y. By transitivity, we have Z is related to y. And so, yes?
I think lemma is not complete. Is it?
What?
Lemma is not complete. Then for any we pair either this or that.
Sure, it is complete. What do you mean by not complete? It is complete now, with the full stop.
Like, the conditions are given, like if, then something should be, isn't it?
No.
Like the structure is like, it looks like it's incomplete.
No. Why does it look like complete? This is my setting, this is my hypothesis. I'm claiming that under this hypothesis, the following sentence is true. For any x, y, and x, the following happens. Okay, if you want, I can write this. If x is in an empty set, blah, 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 blah. Are you happier? Okay. Anyway, and so y is related to x, therefore z is in the equivalence class of y. This shows that equivalence class of x is in subset of equivalence class of y. Now by symmetry, by a symmetrical argument, we also have the other direction. I'm not going to do the symmetrical argument because it's literally the same. It's just a symmetrical argument. Thus, we prove that these are the same. Now, case 2, X is not related to Y. This is a shorthand for xy is not E, the ordered pair xy is not E. Anyway, we wish to show that these equivalence classes are disjoint. Assume not. If these are not disjoint, then there exists some element which is in the intersection. This is by definition of this being non-empty. But then, by definition of equivalence class, x is related to z and y is related to z, and so z is related to y. What? Oh, no questions. Now, by transitivity, this gives. I mean, I'm kind of being stupid here, but I defined in a specific order, right? So I'm using that order. Even though by symmetry I can flip it, I just do it all the time within the proof because this is like the first proof about equivalence relations we do. I'm not gonna be this detailed. Like I'm not gonna put this much effort into detail in the following weeks. By transitivity, this gives what? X is related to y, which is a contradiction. Okay, this contradicts with the case assumption. So, given two equivalence classes, either they're the same or they are disjoint. Now, what this implies is the following. Pick a set. Let's say that you have an equivalence relation on it. You look at the equivalence class. You take any element, you look at its equivalence class. Okay, I have this element, I have its equivalence class, it's over here. And let's pick some other element. I pick this element, I look at its equivalence class. This equivalence class is either identically this one or it's disjoint. Now pretend that I do this for all elements, which there may be infinitely many. But pretend that you can do it like for all elements. At the end, what you will achieve is that you will somehow decompose your big set into equivalence classes. And that's going to be called a partition of this set. Okay, so let me define the partition of a set. Let X be a set and S be a subset of the power set of X. So S consists of subsets of X. Now, this is called a partition if it satisfies the following properties. All elements of S should be non-empty. The elements of S should be disjoint, and the union of S should give us X. Okay? When this is the case, you call S a partition of X. Why is it called a partition? Because like it parts X, okay? It decomposes X into parts, which are disjoint and which together give you all of X. Now, one more definition. Let X be a set and E be an equivalence relation on X. Remember the process I told you. We're going to pick an element and we're going to look at its equivalence class and we're going to pick some other element and so on. So at the end, like we see intuitively that my big set consists of all these equivalence classes. So I should be able to, like, I'm going to form the class of all equivalence classes. And that's going to turn out to be a set. Anyway, let X be a set and equivalence relation. The quotient space, the quotient of X, how did I name this in the notes? Let me look at this. The quotient set of X with respect to E is the set of all equivalence classes. Now, why is this a set? Look at the definition of this. This is the set of all y which are members of X related to X under E. You can easily show using the axiom of separation that this is a set. Like this is supposed to be a subset of power set of X cross X or something like that. No, power set of X or power set of X. Something like that. You can like expand this definition up. You'll see that this is a set by the axiom of separation. Now, let me state the following theorem, which is going to say that the quotient sets are always partitions. Theorem. Oh, now, when you have the empty set and the empty relation, this is empty. And what if X is empty? When X is empty, the only collection of sets satisfying these properties is the empty set again. So empty set has only one partition, namely the empty set. So just to avoid stupidities, I'm just going to start with an empty set, and let's take an equivalence relation on X. Then the quotient set of X with respect to E is a partition of X. Now the proof is easy. How many minutes do I have? I have 5 minutes. Note that, okay. Note that for all X in X, X belongs to equivalence class of X. And so, what this shows is X is a subset of this union. Okay? Each element of X is seen in an element of this set. When this union is the elements of this quotient space, so we have that. So we have this. Clearly, the other direction holds because the elements of this guy are, like what are the elements of this guy are the equivalence classes. The elements of those are elements of X. So we have this. Therefore, we have the third property. And hence, we have the third property holding. Now let's check the second property. We have, by the previous lemma, now if you pick two different equivalence classes, we just proved over here that they're either the same or they're disjoint. No one is stopping me. Obviously, this is false.
If a
Exactly. I mean, you should fix these typos. Remember, we are being watched. So, by the previous lemma, if you pick two equivalence classes which are not the same, we have that they're disjoint. So the second property is satisfied. And the first property, well, this is satisfied because of this. Okay? So, like each equivalence class is non-empty because I'm working with a non-empty set. Okay. Therefore, this is a partition of X. Now, a little exercise. Okay, I have 2 minutes. I can pull it off in 2 minutes, I guess. So what have we shown? If we have an equivalence relation, we can get a partition. The converse is also true. If you have a partition, it actually comes from an equivalence relation like this. Let S be a partition of X. So it satisfies all the properties I just erased. Then the relation E sub S defined by two things are E sub S related if and only if there exists some D to which both of these guys belong is an equivalence relation on X. So let's prove this very quickly. Next lecture, I want to start with that cool puzzle that I talked about. So this is why I want to finish this in this lecture. Okay. The claim clearly holds when X is empty. Okay. For empty set, this is clearly true. Empty set only has one partition, namely the empty partition. For empty partition, you get the empty relation, and that's the only equivalence relation on the empty set. Now, assume that X is non-empty. And let's choose 3 elements. Not necessarily distinct, obviously. I'm just naming 3 guys. They might be the same object. And let's assume that X is related to Y under this relation and Y is related to Z under this relation. Now I want to show that X is related to Z under this relation. Why does this hold? Now by definition, there exists some guy D in S such that these are both in that D. Similarly, there exists some E, let's not call it E, F in S, such that these guys both belong to F. Then, since S is a partition, we have the following. Now, I have an element of this partition which contains Y. I have an element of this partition which contains Y. So these are not disjoint. Therefore, they are the same. And so, if they're the same, then there exists an element of this partition which contains X and Y. Sorry, X and Z. So I have that this relation is transitive. Now, I ran out of time, so I'm just going to do what many mathematics textbooks do when they're too lazy. We have just shown that this relation is transitive, that this relation is reflexive and symmetric is left to the reader as an exercise. Okay, I mean that this is symmetric is obviously because the operation of conjunction is symmetric. That this is reflexive is it follows from the third property of being a partition, namely the union of S is X. Okay, so show that. Now we introduced equivalence relations, and we introduced quotient space, we introduced partitions. We have proven that for each equivalence relation, the corresponding quotient set is a partition. And given a partition, I can form an equivalence relation. I didn't write on the board that these processes are inverses of each other. I'm going to talk about that next time. And after that, we're going to talk about transversals. A transversal will be a set which somehow chooses one element from each equivalence class, given an equivalence relation, and using that we're going to solve a nice puzzle where we are going to have infinitely many prisoners. They're going to be executed if they cannot succeed something, and the puzzle at first sight sounds as if there are no solutions to that, and we're going to see that the axiom of choice actually provides a solution because it implies the existence of transversals that we're going to learn next time. Okay, so I kind of rushed this lecture because, I mean, how many of you have seen this notion? Have seen these notions before? I guess all of you. Okay, so this is why I rushed it, but it's good that we're going over these. These are going to be important notions in future. Okay, this is why I'm going over these. I could have simply said, okay, you know equivalence relations, let's just skip, but I'm not doing that because we are going to be using these notions a lot, like the quotient spaces and so on. Okay, so just go over these, and next lecture is going to be very fun. Okay, so I'll see you.